we're at the Brazos River. We can't do much actual sedimentology here today because of the height of the water, but what we're going to do is stop here and use it as an introduction anyway, and then we'll talk about the river. So today we're not at the stop one that's up there near Houston. We've come down a little bit farther than this stop one. So our stop one, we've left Houston, and we're stopped right here on the Brazos River, which is a meandering river. So remember that sea level rises and falls about every 100,000 years during the last couple million years. So as global eustatic sea level goes up and down, the coastal systems of all of the world's shorelines respond, as does this shoreline. So about 120,000 years ago, shown here, about 120,000 years ago, sea level was at plus 5 meters. It was higher than it is today. We're going to look for that on our way home in the afternoon. Over about 100,000 years, sea level fell. It reached minus 120 meters, meaning it was significantly lower than it is today. And over the last 20,000 years, sea level has risen. As sea level has risen and fallen over time, the Brazos River has responded. So we're looking at the modern day river, but as you recall, during the falling stage of sea level, meaning all of this time from 120,000 years ago to 20,000 years ago, this river still had to reach the shoreline. And as the shoreline moved farther and farther offshore, the river had to keep up with it. And so in order for this river to reach the shoreline farther and farther out, it had to travel farther. It also had to reach a lower point, because as sea level moved out across the shelf, the shoreline was moving out and down. And what that means is that this river had to incise. It had to erode. It was cutting a valley and cutting down and moving sediments farther and farther offshore and causing erosion here where we see it today. So who remembers the difference between a channel and a valley? Are they the same thing? No. Okay. Which one's bigger? Valley is bigger. The channel is a single period of the river's shape. The channel represents one geometry in time that the river occupies. It can fill with water, and it can flow on a regular basis. Now, unfortunately, today the Brazos is almost at flood stage. This is not flood stage. I checked the gauge this morning, and we're about 3 feet below flood stage, meaning flood stage is right around where we are. That's the channel. The Brazos River today is within its channel. It's very high. We can't, unfortunately, go down there and collect sediment in the point bars. It's high, but it is within its channel. So where's the valley? The valley that's bigger. Yes, this is the valley. We are in the incised valley of the Brazos River. So we know already that the Brazos is a meandering river. Which side are we on right here? Are we on a point bar side or a cut bank side? We're on the point bar side, you're right, and there's a variety of ways you can tell that. So here, we are on the depositional side. That means the other side of the river is eroding. The other side is the outside of meander loop, just like on a racetrack. On the outside loop, you have to go faster. It's a longer distance. The water travels faster to keep up. So look at the logs going down. Water's very high today. We'll talk about those logs again later, but I'm really glad you can see an example today. So the water is traveling faster on the other side, and therefore it's causing erosion on the other side of the river. You can look across when the water's lower and actually tell that that side is eroding. The underside of the bridge is being undercut, and there's a whole bunch of riprap now piled around the bridge pilings to protect this bridge. So the water is eroding on that side, and it's slower on this side, and it's therefore depositing sediment here. As you know, a point bar fines upwards. If we were able to dig through the point bar here, the closer we got to the center of the channel, as we walked to the water, we would find coarser and coarser grains, and it would fine upward away from the channel. So that means that the point bar is being actively deposited at a range of levels. Right now, there's no sediment moving here because it's subaerial, but there's sediment moving just into the water. But there's sediment moving all the way across the channel. In the deepest part of the channel, in the thalwag of the channel, the coarsest grains are moving today. And as we come farther and farther towards where we are, finer and finer grains are moving. So if you make your lithologic log or take a core of a point bar deposit and you find that that fining upward sequence, you go from the coarsest grains, the trough crossbedding at the bottom, on up through finer grain sands and ripples, maybe climbing ripples at the top, it's getting finer and finer upwards. But all of those environments exist at the same time in three-dimensional space. In one core, you'll find them fining up, younging up. But we can also think about them existing at the same time if we think about the finer grain structures over here and the coarser grain structures over there. So when you think about the point bar deposit, remember that it's not just your fining upward sequence in one single location, but it represents a range of environments over time. In any real point bar deposit, it's very rare that you'll get that perfect fining upward sequence like the cartoon. This river does go up and down a lot. It's unfortunately been high a lot this fall, making it difficult to access, but it is always going up and down. Remember I told you the Brazos River has its headwaters in New Mexico. So this river is about 1,400 miles long. Do you see how it's sort of brownish red and cloudy water? That's characteristic of the Brazos. The Brazos, unlike, say, the Rio Grande, almost always has this color to it. The Brazos has a very high suspended load. The bed load are the coarser grains that move along the bottom of the river. The suspended loads are the fine grain particles that move in suspension and stay in the water column, even like right here where the water's barely moving. So the Brazos characteristically has a very high suspended load, which keeps it this brownish red color. Not all suspended loads are brownish red. The Mississippi is gray, and that's based on the clay chemistry. Some rivers, like the Brazos, happen to run over red beds, clay-rich deposits, and therefore pick up a lot of red clays. The Rio Grande is moving over different types of rocks and therefore picking up dominantly quartz sand and not a lot of clay. So how high do you think this river does get at its flood stage?
Past the bridge.
Past the bridge, that's exactly right. So the last time this river was above the bridge was 1992. That was a major flood event for the Texas coast. Of course, there have been other major rain events in Houston since then. We've had Harvey, we've had Tax Day floods, we've had Memorial Day floods. I don't remember all the names of the different floods. But in general, those have been urban flooding events. Of course, Harvey was a major event, but it was down by the coast. Remember that this river starts in New Mexico. In order to make it go all the way to flood stage at the highest levels and fill its valley, we don't just need rain at the coast, we need major rain events across the drainage catchment area. So in 1992 was the last time this river reached its major flood stage. The water covered the road level, and water, therefore, was flowing all through here. So today, while we're standing here, yes, this is an erosional area. This is subaerial, and therefore, if it were to rain a little bit, sediment would wash into the river. But at other times, when this river is higher, we have sediment being deposited through here. And the same is true where we see this shallow water right here. Right now, there will be sediment deposited there, but as the water level recedes, the flow slows, then we have deposition of sediments all through this side. Now, the shape of the channel is not symmetric. Here, while we're on this side, the point bar side, the depositional side, the inner part of the bend, we're also on the flatter part of the channel. So if I were to draw a cross section from right here to the other side of the channel, it would go down gradually into the channel and then up steeply on the other side. The channel is not symmetric. That means that at any phase, whether we're at high water or low water, the deposition is more likely to occur here because we have that long, flat, or gently sloping side here for deposition to occur. On the other side of the channel, it ramps up very steeply, very suddenly, so that the water level will move up and down, but without much aerial change in where the shoreline is. And therefore, there's almost always erosion over there. Neither at high water nor low water are we depositing on the other side. So which way is this river moving over time? Absolutely, it's flowing towards the sea. Which way is it meandering? That way, okay? In Texas, property lines are often defined as the center of the river. That means these property owners over here are gaining land. Maybe their fences are being covered up by sand, but over time, at least over generational scales, these property owners on this side of the bend are gaining land as the river fills in this way. The property owners on the other side are losing their farm. As that side erodes, they just own less and less land.